first lecture I talked about supercomputer cooling, and I talked about a current system in which flow boiling at low temperature occurs just on top of the active chip sheets, where a lot of microprocessors are embedded. So the cold air becomes hot as it negotiates. Then as it goes past the tube bundles of flow boilers, it becomes cold. And the vapors of all these flow boilers are collected. Then the cooler air gets warm up again, and then another set of exit evaporator tube bundles, it becomes cool. So you collect the cool air and recirculate it, or you can let that go. That part is not under discussion. But what we said was that this refrigerant liquid flow and vapor flow can be all connected. The system design is not particularly important at this point. So in these situations, if I wanted to replace those flow boilers from an all liquid to all vapor or part liquid vapor with innovative boilers, the kind that we have in say several rectangular cross sections, and suppose I could build each one of them at 50 watt per centimeter square without pulsations, okay? And I had enough length, I knew my incoming mass flow rate, outgoing mass flow rates. I can, by dialing in pulsations, I can go from 50 to 500 watt per centimeter square. I can also build my steady version of the flow regime at 50 to 100 watt per centimeter square, and then dial in the pulsations as needed and go to 500 to 1000 watt per centimeter squares. The thin liquid film would remain stable even after pulsations, but I'll have to increase the liquid flow rate, and therefore that would increase the vapor flow rate at the higher heat fluxes. So you must choose the lengths so that not only it operates at 50 watt per centimeter square, and then you go to 500 watt per centimeter square, and the vapor speed is so fast that you are getting compressibility effects. That's not right. Okay. So what you have to do is you make sure that both from 50 to 500 watt per centimeter, the qualities are such, the gap height is adjusted, the length is adjusted, so you can cover a whole range of heat fluxes. Okay. And quick and dynamic response. So that is the kind of goal and dream for which all this work is being done. But what I'm trying to show here is that even if, so if you remember that connection, then whatever calculations you're doing can relate to building such a flow boiler and flow condenser approach. This I'm just showing for one tube, but there will be a lot of these test sections or staggered things can be connected and done together, for which in my team I have system designers who are willing to help out, particularly from Purdue and others places. So you have a group of engineers, who are system type people who a lot of system engineering thing, but they can do what we can do from an experiment fundamental point of view, but we can come together and we do this. So that's the goal with which I am working on this. So with that said, having refreshed your memory, okay, to what I did earlier, I want to go back to the design problem, and hopefully you would look at the design problem with interest. It's not just a textbook example and I'm making you do because all these correlations exist in the book. But what I'm trying to say is that all these correlations that exist in the book, with some judgment, can be put to good use. And just as I'm doing it for this problem, you can do it for many other problems. Okay, so we had looked at a R123 boiling it started looking at this problem So my cross-sectional area is 5 into 10 millimeters squared. G is 300 kilogram per meter squared per second, which is a rather large mass flux. And notice for this kind of large mass fluxes are needed for very high heat loads. And clearly, even higher mass flux would be needed if I am going above 50 watt per centimeter squared. So m dot in, the mass, total mass of the liquid that's coming in is 300 times 50 times 10 minus 6 kilogram per second is the rate at which mass is coming in. So that is 150 times 100 into 10 raised to the power 4, 10 minus 6 is 1.5 kilogram per second is the rate at which refrigerant is coming in, okay, at the inlet. Do you see that? The question was, what should I choose X in equal to what, such that I know my m dot liquid in and I can put my design tube here to pump the right amount in the right order of magnitude, and m dot V in we need to plug in such that m dot L in and m dot V in are known. That is only one of the things. And the flow is annular. So my liquid film looks like this, and I have a situation where some liquid is still draining out. It's not all dried out. That's another requirement. And I need to know the length is equal to what. So we have some such that m dot L out is still not 0. It's greater than 0. Delta X out is, say, 1/10 of 1/5 of delta in. I want delta in to be of the order of 300 microns or less. So all these put a lot of constraints. And if you just say, no, I want to do a micrometer scale boiling and condensing flow, so I will start with 100 micron and 50 micron diameter tubes. What's going to happen is that you may fulfill your desire that you did experiment, but you will have huge pressure drops and a lot of problems in realizing any goal. So what I'm trying to say here is you need to know what your goal of the experiment is. If the goal of the experiment is what happens in 100 microns and 200 micron tube, fine, you can go ahead and do what many people are doing. But if the goal of the experiment is to cool some device at a certain heat flux, certain heat load, and that it be energy efficient, then what is important to be micron and submicron scale is the liquid, not the cross section of the tube, if you can help it. Okay? Those are the constraints. That's the reason for doing these problems in millimeter scale, which are neither too big nor too small. So the first question was, find the length, find a X inlet quality such that the flow is annular, and also and L such that X out. In this case, the problem has been reduced to something which is no more than 0.75 of the total mass has gone into vapor. Okay? Those are the constraints. So we had gone through this. First, what I did was I applied annularity conditions of, we computed the fluid properties, we computed the non-dimensional numbers that are in play under these conditions. We computed assumed an inlet quality of 0.01 or just any quality of 0.01, and found out that that's not going to do because it's not satisfying this number V star is greater than 7x. So we started iterating, increasing the inlet quality from 0.01 in steps until we reached 0.0283 when Weber star became equal to 7x. So now that was my result according to Kim and Mudawar micrometer scale correlations. The result didn't make sense, perhaps because much of his data was biased towards 100, 200 micron diameter tubes and less to the higher diameter tubes, or whatever else. There might be some other reasons behind it. So since we cannot trust a journal paper's correlation by itself, we said let's look at adiabatic flow. And since particularly when you come in off the splitter plate, and even if you put it all at a uniform heat flux of 50 watt per centimeter square, for a short region after it negotiates the splitter plate, not much heat has come in, okay, to evaporate it, because previously it was just warming up the liquid slightly. So it would be close to adiabatic. At that liquid flow rate and that vapor flow rate, you can ask what is the void fraction, what's the film thickness using adiabatic correlations, and you may be reasonably good, because only after a certain distance would the thicknesses and cross-sectional areas of the liquid would start reducing from that of an adiabatic flow. So with that in mind, we said let's look at an adiabatic flow regime map and look at this Mandan-Hane, and near the inlet at least I should be able to get a value of the inlet quality. So we computed the superficial velocity J sub G, J liquid, because that's what he used in his chart. We found that my J sub G was between 0.1 and 1.46, which corresponded to 0.1 and 1.46. If you look at the curve fit, it is in this part of it. So we said you have to be less than that. So let's look at J star L, and it turned out for an assumed value of inlet quality, it wasn't here, but it was above that. So it was a plug slug flow. Okay, so we found out that 0.01, if I start for the inlet quality, and even if I do that, then I get a non-annular flow. So I kept on increasing the inlet quality until I reached a value of JL, which is greater than 0.155, and that value turned out to be 0.3065. So we're looking at these 2-3 correlations. I am confident that if I come in at more than 0.3 under these conditions, I will be okay at the inlet as an annular flow. You can also find out what the film thickness is, but I'll discuss that after a while. And because you also want the liquid when it comes out of the splitter plate. If the splitter plate is around 300 micron and it comes out, you want it to be not only annular but remain around 300, 250 micron, not suddenly go to too low or too high a film thickness, because it's going to self-seek the liquid vapor interface. It's not going to be like separated by the plate. Okay. So we found that 0.4 will do, 0.4565 exit quality is X out, and it's a uniform heat flux method of heating. So you know that it's the quality is a linear variation. So we say X out minus X in by this non-dimensional distance L by H equal to boiling number. You know your X out, you know your X in, you know H. okay, 5 millimeter. You know your boiling number, you had just computed it, you will find the value of the length, which is what we did. So we found that a 14 centimeter long will give me annular flow and a quality variation like this. Now I want to make sure that I boil at a reasonable temperature so that my T wall is above T sat, but my T wall should not be more than 70, 75, 80 degrees Celsius if it's going to be used for electronic cooling. That's one of the reasons we chose R123. I could have chosen water, which would have been even better. But the other constraint was that I wanted to operate at inlet pressure above atmosphere, and I wanted to get out above atmosphere because the system which is above atmosphere is a lot safer. If it is below vacuum, you have to have much more sophisticated technology for no leaks, and you cannot guarantee it. And if there are leaks of air coming in over a long time, none of these correlations work anyway. As we saw in Professor Ghosh's thing, how condensing flow gets completely different even with 1% of air mixed in it, because of the diffusion related issues. This problem obviously doesn't exist in heat pipe, which I discussed last time, because you have a single sealed tube completely evacuated. It would remain more or less that way for quite some time, okay, decades.